Hello everyone, welcome back to Labtube. In this video, I'm going to do question 2 from section 16.4. The question asks to evaluate a line integral for a vector field in two ways. One, directly, using the definition of the line integral, and two, using the Green's theorem. What is the line integral? In this case, the line integral is given by this, and the curve is the circle with center, the origin, and radius 4. Okay, so let me recall first how to evaluate a line integral of a vector field along a curve. So first thing would be, okay, so you have a vector field along a curve parameterized by r. Then the way you do that is that, to evaluate directly, is that write everything in your parameter, meaning that plug in RT in your vector field, put boundaries of t in your integral, and then dot product this f along that curve by r prime t. Then you get a function of t, then integrate that function. That's just how we evaluate directly. 2 would be if you have a curve C, which is simple, which is closed, and which is positively oriented, then f dot dr, other way of writing this would be first component dx plus second component dy. This is equal to a double integral over the region inside the curve d, and the integrand is dq partial derivative of q with respect to x minus partial derivative of p with respect to y, and then integrate that double integral. Okay, so those are the things you need to know for this question. What is our vector field for this question? So here I have the coefficient of dx is my first component, and the coefficient of dy is the second component. So I have that, oh sorry, the first component here is y. Okay, we have that. And then what about the curve? Curve is the circle. Okay, let's orient that positively. That means counterclockwise. And then the radius is 4. Okay, to evaluate this integral directly, the first thing is that I need to find a parameterization for circle. Good parameterization for circles centered at origin is given by polar coordinate. R, in this case, the radius is 4 cosine theta, and 4 sine theta for y. And to cover the whole circle, I have to vary theta from 0 to 2 pi. Okay, that's the parameterization I'm going to use. But to evaluate this line integral, I need to know what is r prime. R prime theta, the derivative is negative 4 sine theta for cosine theta. And that's something that I'm going to use now. Integral over c f dr is, put everything in terms of your parameter. In this case, it is theta. So you put boundaries for theta, go from 0 to 2 pi. And then f, plug in your parameterization in your vector field. So y for me is 4 sine theta, and x is negative, x is 4 cosine theta. So second component is going to be negative 4 cosine. That's f. R prime is negative 4 sine theta and 4 cosine theta. You dot product these two, you're going to get a function, then integrate that function with respect to theta. Okay, let's see how this goes now. Dot product this times that, it is 16, negative 16 sine square theta. And this dot that is negative 16 cosine square theta d theta. Oh, that's good. Now I can factor out negative 16, and the remaining part is sine square plus cosine square, which is equal to 1. And this gives me integral of negative 16, which is negative 16 theta, go from 0 to 2 pi. And when you do that, you get negative 32 pi minus 0. Okay, that was just direct computation. Now, let's do the Green's theorem. Okay, in this case, in this case, I have to change my integral from line integral into a double integral. Double integral over what? Over the region inside the curve. For this case, I have the region, it's a disk of radius 4 and centered at origin. But we know that integration of circular regions is easier to done in the polar coordinates. So it is better to write this region in polar coordinate. So theta, as always, should go from 0 to 2 pi to cover the whole circle. But r goes always from 0 to the radius of the circle. So r goes from 0 to 4. Okay, that's the region. I'm going to evaluate double integral over that. But what is the integrand? The integrand is dq, find partial derivative of q with respect to x minus partial derivative of p with respect to y. Okay. dq is this, q is this. dq with respect to x is negative 1 minus p is y, partial derivative of p with respect to y is 1. Sorry. So I have negative 1 minus 1 dA. That is a double integral. Then I have to make it into an iterated integral. So I already did some parts. I found the boundaries in polar coordinate, so then I can go ahead and do the polar coordinate. Integrand is negative 2. The line integral in polar coordinate is r dr d theta. So I go from 0 to 2 pi. Antiderivative, I'm doing it inner integral. Antiderivative of negative 2r is negative r squared. Go from 0 to 4 d theta. And then 4 is negative 16 minus 0 d theta. And then negative 16 with respect to theta is negative 16 theta. Go from 0 to 2 pi. And this is going to be negative 16 times 2 pi minus 0, which is negative 32 pi. So that's the way we do using the Green's theorem, by changing line integral into a double integral and then evaluating that double integral. Note that the method we are doing should not change the value of integral. In both cases, we get the same number. That was it, and thank you for watching this video.